Okay, go ahead and get set up. We'll get started in 1 minute or so. Okay, well, if anybody shows up late, I guess they can catch up. So just to let you know where we are in the semester, and let me make sure this is streaming without any dropped frames. Perfect. Okay. We're going to do the midterm in 2 weeks. So today is actually the start of week number 7. So that would mean that we're going to do the midterm on week 9. And what I usually like to do is a short review. So mark this on your calendars or in your memory, or just know where to find this under announcements. Okay. Now I'm not going to go over most of the details today. What I'll do is when I do the review, I go over the details, but it's a pretty straightforward exam, especially if you've done the assignments. It's just a multiple choice exam, and it's based directly off the assignments. So anybody who's been getting A's on the assignments or high, 95 or above especially, you should be able to do okay on the, as long as you've been doing your own work, you should be able to do okay on the exam. I'll confirm next week, but I'm fairly certain that I'm just going to do up to assignment number 4, which is what's due today. So before we leave the midterm, very briefly, is there anybody who knows that they're not going to be here in 2 weeks? I think this class, I think everybody's been pretty much showing up. I think we have like 10 registered people. 5, 6, 7, 8. Yeah, almost everybody. For anybody watching at home, if you know you're not going to be here in 2 weeks or be able to make it on campus, last I checked, I'm pretty sure the testing center is still closed. Has anybody taken a test in the testing center? I imagine it's still closed. Yeah, it's probably still closed. So if you're not going to be here, I can't just send you to the testing center to take it at another time. We got to come up with some other arrangements. And the exam, just to be clear, the exam is in class at the regular class time. Sometimes I get that question. I think at other universities and transfer students and stuff like that, sometimes they're used to taking it in some other room or something like that. It's just normal class time. And we'll go over more of the details next time. But assignment number 4 is due today. I saw a few people turn this in. For the people that turned it in, were there any parts that maybe I should go over that maybe I didn't go over as much in class? I'm thinking maybe interrupts I need to spend a couple minutes on just to be sure. Okay. And then just to note that you have a new assignment here, assignment number 5. So do your usual thing where you copy and paste this into a Word document, because we're going to go ahead and start this today. We might be able to get through the whole thing or most of it. Note also that I put it on as the due date on Friday, so in 10 days. So not this Friday, but in 10 days Friday. Actually, I guess 9 days. The reason I did that is because I've done this in the past where I make assignments due the same day as the exam, and then I get a lot of people who can't really, remember to worry about an exam and an assignment at the same time. So that's why I broke them up into 2 different due dates. Okay. And we'll go over all this in a little bit. A lot of this we've actually already gone over in the early chapters, but anyway. So let me briefly talk about interrupts. Their diagram isn't the greatest on this. but it gives you a kind of a general sense of what happens. Normally when I'm running a program, I execute things in some sort of order of importance. So I think a lot of people play games, so you might think of a game. Like if I press, well, let's say, probably not a good example because games are full of interrupts. So I want to give an example without a lot of interrupts. If you've got a program that is doing a lot of calculations, what we call batch style programs, where we start the program, it has a very clear goal, it has a very clear thing it needs to do. For example, if you're doing a calculation on, let's say, for example, a weather simulation. And you know how the National Weather Center, they always do those simulations of where the hurricanes and tropical storms are supposed to go? That's a very good example of a batch calculation, is that they gather all the inputs, all the weather conditions, they let their algorithms run for a few hours or however long it takes them, and then it gets a result. And that was the style of programming that we did for a very, very long time. But once we started to create systems with keyboards and mice and computer networks, certain things are very high priority. So going through our timeline of operating systems, we had batch style programs where you can think like a weather simulation where we run a program from beginning to end. We realized that many times the program's sitting there doing nothing. It's waiting on a slow hard drive, which we're going to talk about today. There's this like pyramid, but the idea is that CPUs are very fast, but they have a very small amount of memory. Just make sure this didn't cut out. Okay. Sorry for always checking that. I've just had semesters where it's like halfway through the lecture, it just cuts out and I don't really get notified, especially if I get full screen PowerPoints. So we have these batch style programs that run weather simulations. And the next phase was, okay, I'm waiting on the hard drive for a very long time. The CPU is sitting idle. So the CPU is very fast, but it has a very small amount of memory, basically in the order of bytes. Hard drives, on the other hand, are at the other end. They're very slow, but they have huge amounts of storage in the order of terabytes. So a gigabyte would be billions of bytes. Terabyte would be trillions. And the idea is that this hard drive is feeding data to the CPU. The hard drive is very slow. CPU is very fast, but it can only hold a few bytes of information. So that time that it's sitting there waiting for information from the hard drive, we realized that we can run multiple programs at the same time. That's where we get the idea of an operating system. And so remember we had that orchestration picture where it coordinates all the things that need to happen. It says, okay, well, you're waiting for the hard drive. I can stop this program while it's waiting for data from the hard drive, and I can start running another program. As time went on, our computers got more sophisticated. They were no longer running these batch jobs. We had what are called interactive programs, where I have a keyboard and mouse. Interactive program, you can think of like a game or a Microsoft Word. And if I'm playing a game, let's say a racing game, and I send a control to accelerate, do you think it should wait its turn, or do you think that button press should be handled immediately? Imagine a game where you press a button and then maybe a half a second later it registers. That wouldn't be a very fun game. Even though a half a second is, relatively fast, it's still a half a second. You want that thing to be handled immediately. And that's where we get the idea of interrupts. Same thing with a Word document. Imagine if you're typing and you press a key and then there's a small delay, which was actually early computers were so slow that was very common. But these days we don't even really think twice about it. We press a key. And this is the idea of an interrupt, that something is so important that we can interrupt everything else that's going on and we can handle that immediately. Because because that's such an important thing, we want to interrupt everything else and handle that immediately. Now, we shouldn't get caught up in the idea that it's just for keyboards and mice, because there actually are other things that may interrupt our system. Again, going back to a game, imagine that we get a frame update or some sort of update if we're playing like a multiplayer game. we probably want to see the new position of the other characters in this multiplayer game. We probably want to see it right away. We don't want to wait a half a second. Imagine a multiplayer game where we had these giant latencies of characters going across the screen. Anybody who's played a multiplayer game with a lot of latency probably understands why it's not fun. And so that might be another example, but we're not getting our frame updates from the keyboard or mouse. We're actually getting our frame updates from over the network. Okay, so there are instances where interrupts can be from the keyboard and mouse, but you can actually get interrupts from the network. There's a bunch of different ways to interrupt. Imagine if you're running a clock. So your motherboard actually has a built-in clock, and it keeps your operating system's, the software clock, up to date. And so what happens is that every, let's say, millisecond, it sends some sort of update. That's probably a little too fast. Let's just use a round number. We'll say every second. Every second, what it wants to do is interrupt. Imagine a clock where you're off every second by, let's say, a couple hundred milliseconds. Well, over time, that's going to add up. You're going to have a clock that's not very in sync anymore. Okay. So interrupts very often happen from events from a keyboard and mouse or other input device like a game controller, but it can happen from anywhere, even from your hard drive. Let's say, for example, I ask for a piece of data. I don't typically want to lock up the system. What I want to do is say, okay, give me this data. When you get it, call a system interrupt. And so the hard drive might say, I have this piece of data ready. So many, many different sources of interrupts. And remember in your head the two types of, if you're doing batch style programming where it's just running beginning to end, we don't really have to worry about interrupts. But once we get these very sophisticated programs that may be interactive, where I'm interacting with a computer or other things, many times that we don't know when this thing is going to happen. I could sit here waiting for it, but we know that eventually somebody's going to press a key on the keyboard. It could be a half a second from now. It could be 2 days from now. You might just leave your computer up and running, if you just forgot to turn it off. We don't want to have a program running in the background just waiting for people to type on the keyboard. What we want to do is say, okay, when somebody types on the keyboard, there's a special piece of hardware on your motherboard that it can generate an interrupt. Okay, are interrupts a little bit more clear now with that explanation? Okay, were there any other things before we move on that might have been a little bit unclear? Is everybody good on file systems and file extensions? And then the idea of drivers. So I'll very briefly go over drivers just one more time just to make sure everyone's clear on those. So there's this very small part of the operating system called the kernel. It's the very, very core part of the operating system. And the idea with the kernel, you can see here, the kernel kind of, so many times when people think of the operating system, they think of like Windows or Android or iOS, and they think of the graphical applications and the web browser and all these different programs that are associated with the operating system. But in practice, the actual part that does most of the work is called the kernel. The kernel is what does the task scheduling of, remember I told you like I have 2 programs and the program's allowed to run for a certain amount of time, and the kernel handles all that, all the interaction with hardware, you can see here. And it sits as this, what we call an abstraction layer between your applications. So your applications would be Microsoft Office, any games you're playing, maybe like a media player, like a Windows Media Player or something like that. And so those are what we call user land operations or user land applications. And then so we have kernel space and user space. Now the idea is that the kernel is the thing that manages everything. And what's nice is that because we can kind of segment off applications into their own space, if an application crashes, the kernel is actually a separate program, and the kernel can detect, okay, this program crashed. It's not responding. I'm sending it things to do, and it's not responding. So the kernel can actually kill or end that process. Now, the problem is that what happens when the kernel crashes, because the kernel is handling everything. So imagine going back to that orchestra analogy. A single person can stop playing their instrument for a minute for whatever reason. Maybe they have to cough, whatever. But if the conductor stops, that's really going to cause a lot of problems. That's kind of what happens with the kernel, is that once the kernel crashes, it's very difficult to recover from that. There's been a lot of research and other things, but once there's a kernel crash, it's very, very difficult or impossible to recover from. Now, you'll notice here that the kernel interacts with hardware. And in the early days of computers, when somebody sold you a computer, they sold you the computer knowing all of the hardware that's ever going to run on that computer. So like these very old computers like the Commodore 64, they knew they knew the exact hard drive, they knew exact amount of RAM and how much, or if there were variations, there were very, very tiny variations. With the IBM PC, the whole idea with the IBM PC is that there were these various slots where I could extend the computer. Back then, there were ISA slots and PCI, but we have modern equivalents and even AGP. Mostly, we have PCI Express, most things, and I'm sure there's other various buses, but PCI Express tends to be the most common. Also USB. So the idea is that on this computer is very extensible. I can expand it as needed. The problem is that for every piece of hardware, I need to know how to talk to that piece of hardware. And we do that through the idea of a driver. Now, in practice, there's probably been tens of thousands, maybe even hundreds of thousands of pieces of hardware ever invented if you go all the way back to the 90s or the 80s with the IBM PC. And every single one of those needs one of these little pieces of software called a driver. If we included all those drivers by default in the operating system, we'd have this gigantic kernel, and it would always be kind of very unstable because different softwares at various quality. So what we typically do is the driver is a separate piece of software. And then what happens is when I plug in a piece of hardware, the operating system there's some basic negotiations, and it can say, okay, this is what this hardware device is. Let me look up its driver so I know how to properly talk to it. So it's almost like what we call a shim. It can do a very basic conversation, basically, and say, hey, what device are you? And it'll return and say, okay, I have this ID from this manufacturer, and so on. It says, okay, so I need to get this driver for it. So that's kind of nice, so that it makes it so that we don't have to keep all the drivers always loaded into the kernel. We can just load the drivers that we need to. But there is a little bit of a side effect, because notice to talk to hardware, I do need one of these things called a driver. Because the driver actually becomes a part of the kernel, a driver crash is the same thing as a kernel crash. And as we just said, once the kernel crashes, the whole system goes crashing down, okay? And I think those were the two that I kind of raced through. Anything else? Everyone was able to find this chart okay? This was a research question. We talked about file extensions a fair amount. We briefly went over this question, but it's pretty straightforward. Okay, I think that's pretty much it. Any last minute questions on assignment number 4 before we leave that and go on to number 5? Okay. So assignment number 5 is based off of this chapter on hardware. We've already gone over a lot of the hardware, but this kind of goes into some things in more detail. Now, as usual, like I said, copy and paste this into a Word document, and then as we go through things, it'll make your life a lot easier. So let's take a step back. So we've already, just as kind of a quick review, we've already gone over a lot of things in the initial parts of the course. We went over what a CPU is. Remember, it's kind of we think of it as the brains of the computer. And then our computer memory, that's like a working scratch space, that's like a working area. And then we have our storage device, which is our hard drive. And we take those basic components and we connect them all together onto a motherboard. And then from there, we take that motherboard and we have to put that in a case and connect it to a power supply. And then we had I/O devices, input and output devices that we connect to make the computer a little bit more usable, things like a keyboard and a mouse and maybe even a printer, speakers, and so on. So let's talk about the first item on that list, the CPU. So CPUs are interesting. As we mentioned, we can kind of say it's the brains of the computer. And because of, I don't know if it's dumb luck or whatever the reason, the actual materials used to manufacture a CPU, these little things called transistors, the way they're made, we just happen to get lucky enough that we've gotten really, really good at manufacturing them at the microscopic scale. And we've been able to make computers much faster in a relatively short period of time. So there's this thing called Moore's Law. It's it's kind of a technical definition. It's very often misinterpreted. We'll probably hop over to Wikipedia because they probably have a better. Okay. So there was an engineer working for Intel in the early days. His name is Gordon Moore. And when they were making CPUs in the early days with these transistors, he noticed that the way they are manufacturing them, basically they were getting twice as many transistors in a single area. So imagine you take an area the size of let's say a pizza, and then you count how many transistors you're able to put on that area. And he was noticing about every 2 years you were able to double that. Now, one of the consequences is that the more transistors you can put in that area, essentially you've made a faster CPU. It's a little bit more complicated than that, but that's kind of the end result, is that if you're able to double the number of transistors, they have shorter distances for the electrical signals to go. You can do more complex operations. Many reasons why, but essentially the idea is that essentially you're going to get a computer that's about twice as fast. And he made this prediction very early on. So his name was Gordon Moore, and if you look at the number of transistors on what they call a platter, it kind of looks like a like a pizza. It's circular in nature, and then they cut them up into square slices. And his observation, I think it was more as like a manufacturing observation, but over time what people realized is that as a consequence, CPUs were getting much, 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 much faster. If you look at the CPUs of, let's say, 1970, and then fast forward 50 years to today in 2020, I don't think there's any other industry that you can look at 50 years later and it's like night and day like that. Like even with cars, like the very early cars, if you looked at the number of miles per gallon early cars could get, and then compared to like a car from 1970 to a car in 2020, it's you're not going to be doubling every 2 years the number of miles per gallon. Okay, it got better, maybe even 4 or 5 times better, let's say, just at the very extreme end, but it's nowhere near anything like Moore's Law. Even 4 or 5 times is probably an exaggeration. It might be like twice as good. And then as time went on, he made this prediction in the early 70s. And we can see here, these are various CPUs throughout the time. So this is updated in 2018. And it's pretty much held. So about every 2 years, and actually there's some periods of time where every 18 months. So the one that you'll often see in news stories is actually every 18 months, because there's been periods of time where every 18 months we actually did that. And there's a good video on YouTube that I saw where somebody actually, I don't want to put it because I'm recording the lecture, so I don't know if that's going to cause any issues or anything like that. But you can look it up. It's basically, it shows over time Moore's Law's prediction as different CPUs are released, and it's very, very interesting. It pretty much holds over time. Now, one thing might notice is that it's linear here for a very long time. We have some outliers, but it holds the line. But somewhere around 2012, you can kind of start to see that it's flattening out. There's been some new CPUs, but in general, it's sort of flattening out. And that's because at some point, Moore's law runs out. It's because at some point, you're going to get these transistors that, like, you're going up against the laws of physics and the laws of chemistry. Like, the transistors are going to be like only a few atoms wide, and then at that point, you just can't make a transistor anymore. Eventually, we're going to have to get into what's called quantum computing. I think we're still a little ways away from that. Anybody who follows new tech news knows that Intel's been really, really struggling with this. So you'll see that these manufacturing processes like 14 nanometers and 7 nanometers and stuff like that, they've had a really tough time going to the next generation of making smaller transistors because it's just gotten so expensive and so difficult that to release a new CPU these days, it costs like billions of dollars. It's like the equivalent of, not quite the equivalent of, but almost like releasing like a new pharmaceutical drug or something like that. It's just gotten incredibly, incredibly difficult because it's so complex, and really there's actually only a handful of companies even bothering to manufacture CPUs anymore. There's a lot of companies in the industry, but the number of companies actually making CPUs is very, very, very small. So we see this flattening out. What happened during this flattening out? So very quick summary before we move on. Sometimes I get maybe a little bit too complex. We've got this idea of the CPU. The CPU is the brains of the computer. It does all the calculations. And this guy at Intel in the early 70s, Gordon Moore, was noticing that about every 2 years, 18 months to 2 years, he was doubling the number of transistors on the same size platter. And this is good for many reasons. One of them is because you don't have to throw, if there's like a mistake on one of the platters, you don't have to throw away so many CPU dies. But the other consequence is that essentially is making CPUs twice as fast about every 18 months to 2 years. Now, over time, this has slowed down. Like I mentioned, that there's just laws of physics and laws of chemistry that you just can't get past. And so going back to the previous chapter, one of the things that I kind of waved my hands and told you is that a computer can actually only run one program at a time. And what it has to do is this thing called context switching. So I start a program, let's say for running weather simulations, and that program runs for a little while. It waits for the hard drive, and then it does a context switch. It switches over to a new program because it actually only can run one program at a time. And it does these context switches really, really fast to give you the illusion that it's running multiple programs at the same time. That's not exactly true anymore. So probably about in the 90s, we started to get into systems where you could actually plug in multiple CPUs into the motherboard. Now, those tended to be very high-end server-based, but if you've got 2 CPUs on a motherboard, you can technically run 2 programs at the exact same time, correct? With 1 CPU, I can only run 1 program and I can context switch, but with 2, I can technically run 2 programs. Now, a typical computer is actually running like 100 programs, so we still want to do context switching, but it's kind of nice because we can maybe dedicate 1 CPU for things that are very long running and then very short tasks on another CPU. Okay, so we have that, and so now we can run 2 programs at the same time. Then in the, I'm bad at dates on this, but I'm willing to bet that it was somewhere in the 90s to early 2000s, there was a lot of research into this area called simultaneous multithreading. Now on the CPU is a very complex thing. It has this what's called a pipeline, and the pipeline at various parts is not always active. So what they came up with is a very clever way for on one CPU, what I can do is I can stuff multiple programs into that one CPU, and while parts of the CPU are doing one thing, I can do one thing, so, and the generic technology is called SMT. I still only have 1 CPU, but I can kind of run 2 programs on it. It doesn't mean it's going to be twice as fast, because that's not how the world works, but maybe I can get like a 20% improvement, 30% improvement, something like that, maybe as high as 50%. So it's worthwhile that I can try to run 2 programs at the same time. Now, you've probably actually, many of you have heard this before. Intel ran with this and they actually gave it their own branded name. So does anybody know Intel's branded name for this technology, SMT? It's called HyperThreading. So anytime, how many people have heard of, show of hands, HyperThreading before? Okay, so that's just their brand of it. And you can actually see here on Wikipedia, the second result was actually HyperThreading. And this is the basic idea, is that I've got one CPU, and I can kind of make it run multiple things at the same time. Now, it's not perfect, because, there's other problems. But then what they realize is that, okay, on a single CPU, there's this thing called a CPU die. Or what we'll use the terminology of CPU core. And a CPU core is kind of like, that's the main part of the CPU. And they came up with all these very clever technologies where they could start to put multiple cores on a CPU. And so that made it so that you could truly run multiple programs at the same time on a single CPU. And that's the technology we tend to have today, is that most of you, without even realizing it, probably have a multi-core CPU. The most common, even on laptops, is 2 cores. But once you get into gaming systems and other high-end systems, you start to see 4, 6, and 8. AMD releases a chip called Threadripper, where their only goal is to try to put as many cores on a CPU. They're very expensive. They're like, last I checked, maybe $5,000, $6,000, $7,000 for their top-end Threadripper chip. But I think the highest core count that they have on a Threadripper chip, and this is consumer-level stuff, is 64 cores. And I think the next generation, they're talking about even more. Research-wise, I've seen them put thousands and thousands of cores, but that's like research-level stuff. That's not something you can go out and buy. That's like what Intel and AMD do just to have a press event. They're like, look, we put 5,000 cores on this CPU. You know, it's not stuff you can actually buy. So at the high end that you can buy as a consumer, if you've got some money to burn, is Threadripper. And then I'm sure on the server side. Now, one thing that Intel did is they said, we've already developed this technology called hyperthreading. If I've got an 8-core CPU, I can also stuff this hyperthreading in there and get even more performance out of it. So modern CPUs are very, very complex. That's why a lot of times I like to start the course with a very simplistic view of the world. One CPU that can only run one program at the same one CPU that could only run one program at a time on that CPU. But the modern world is much more complex, is that we've got multi-cores and hyperthreading technology. Intel actually got burned by this because their modern CPUs are so complex that there were a set of security vulnerabilities that happened, and they didn't know what to do with it. They were caught off guard. If there's a bug or an error in software, I can rewrite the software, correct? It's fairly easily. Most of you have probably gotten like Windows updates before. That's essentially what's happening, is that somebody made a bug or some sort of error in the software. Okay, I'll just fix that, recompile it, and send it out to people, and then they can get an update for that. Can you do that with a CPU? Not really. There's this thing called microcode, which is like software, but in general, no. Once you've created that CPU, you're kind of stuck with that CPU. If you've made a mistake designing that CPU, you're kind of out of luck. So what Intel started to do was they said, disable hyperthreading. We don't know what else to do. So a lot of chips, for a while, pretty much any chip you bought had hyperthreading. But now that they get this whole thing straightened out, which is going to take years, a lot of chips, they've actually just disabled hyperthreading. So that whole long story, your main takeaway is that early CPUs could only run one program at a time. Then we came up with this idea of hyperthreading, which is Intel's brand name of it, but the general technology is SMT. And it's this idea that you can kind of use parts of the CPU that are sitting idle to do other things. And so you can sort of get the effect or the illusion that it's running multiple programs at the same time. And it kind of is, but really this idea of multiple cores is that you have a fully functioning CPU core on one CPU package. So if you actually look at the CPU, it's one thing, but it might have, let's say, 8 cores inside of it. Why is that important? Well, this flattening out here pretty strongly correlates to when they started introducing multi-core CPUs. Now, that gets a little bit complicated. If I write a program, let's say, for example, we'll keep it very simple. Let's say for a game. And we'll just, let's say, for example, a racing game. If I write it using my classical training as a computer scientist in a very straightforward manner, and I write it to target one CPU core, and all of a sudden you introduce a 4-core CPU, is that game going to be any faster or any better in any sort of meaningful way? So I've written it to only use 1 core, but I have 4 available. Is it going to be any faster? Not really, because I've only written it in a way, maybe other things can be offloaded from the operating system or something like that. But in general, if I write what's called a single-threaded game, it's going to just use the 1 CPU core. So what do I have to do as a game programmer or developer? I have to go back and decide, how can I break this game up into multiple parts? And I might say, okay, the physics engine is running on 1 core, and the graphics are running on another core, maybe any sort of multiplayer or, game state, or, I can come up with some way to spread it across 4 cores, but then what happens if somebody has an 8-core chip? And so it doesn't really scale. And as a developer, it's kind of difficult to think of rewriting my programs in a way that it scales across cores. And that's very common in the game industry, is that there's kind of a limit. You can't just, if I threw a Threadripper at a game with 64 cores, most likely it's not going to do anything interesting with those extra cores. For Intel and AMD, it's a whole lot easier for them to put more cores on it than try to shrink these tiny little transistors even more. So that's where we start to see a flattening out, is that rather than trying to make smaller and smaller transistors, they said that's expensive. We don't like that. Let's just keep on adding more cores. So rather than scaling in a way that makes your CPU faster, they did what we called scaling out. So you can run more things at the same time on that single CPU, but it requires a modification of the software. So that's kind of where we're at in 2020, is that there's this race where CPUs aren't getting nearly as fast as they used to. At some point, we're going to have to just do quantum computing, because we're just going up against the laws of physics, that at some point we're just not going to be able to make transistors any smaller, because they're going to be like the size of an atom, or a few atoms. And that's why we start to see this flattening out. But this held for a very, very long time. Now, there is something, I actually saw it in the news just the other day. Let's see if I can find it. So it's going to be, yeah, so they're calling it, I don't know how to pronounce it. It's the CEO of NVIDIA. I guess I don't want to mispronounce his name. But basically, there's this idea that on CPUs, Moore's law is flattening out, but they're coming up with very, very clever things on the GPU side, and that the next generation or the next iteration might be, we might have a new version of this related to GPUs. And GPUs are very interesting, because GPUs do a lot of what's called matrix algebra, and so rather than being able to do one task at a time very well, imagine if you had this tunnel where I could send one car through very quickly through a tunnel. Imagine GPUs are like a very wide tunnel where I can send a bunch of cars through, maybe a little bit slower, but that's the basic idea, is that GPUs do a lot of what's called matrix algebra, where I can do a very complex operation. CPUs have always generally been where I can kind of do one calculation. And so long story short is that especially with Graphics cards, oddly enough, are very good at these things called neural networks and AI, because for gaming, I have to do a lot of matrix algebra, and for AI, I have to do a lot of matrix algebra. So that's one of the reasons that NVIDIA has become such a powerful company in the past 10 years, is because all of a sudden, all this technology that they've been developing, all of a sudden it can be also used for AI. And so a lot of people, myself included, who don't play a lot of games might own a NVIDIA video card just to do neural networks and AI related things. So anyway, that's kind of a unrelated thing. Okay, so we just talked about Moore's law and the basic idea of it, how we're doubling the number of transistors on a platter every couple of years or so. We talked about who the person was. We also talked about number 3, this idea of hyperthreading versus CPU with multiple cores. And they actually have, I think, a decent, yeah. Slide. This is kind of a decent diagram of what's going on here, is that with hyperthreading, you're taking that one CPU and you're kind of using unused parts of it. So if you've got a web browser and an antivirus running at the same time, to the operating system, it kind of looks like it's doing two things at the same time. Internally, it may or may not be. But with multiple cores, you truly are running multiple programs at the same time. Okay. Number 1, I don't want to get into too much. Number 1 is kind of tricky. We've already, I think, talked about this enough that we could probably just flat out say the answer. But there's really 2 main companies making these chips. But making is kind of a vague term, because so Intel still actually makes their own chips. AMD, it's a little bit more complicated. They used to. And what they did is their actual manufacturing, because the actual manufacturing of the chips is so complicated, they sold off their own, that unit, and now that into a separate company. I can't remember off the top of my head the name of the company, but when I say 2 major manufacturers, I'm just using it in the very simple sense that we've been talking about so far. You know, of the 2. If we were to go on a Newegg right now, there'd be 2 dominant names for CPUs. It is, like I said, it's actually kind of complicated because there's only a very small number of companies actually making CPUs anymore, because to make one of these manufacturing centers costs like billions of dollars. It's incredibly expensive, and nobody really wants to invest the money into it. So for the most part, if I'm a company that wants to make a CPU, I'll design the CPU, I'll do all the software related stuff, all the engineering related things, but the actual process of making a CPU that I can sell to somebody, usually they offload to these very small number of third-party companies still out there. So let's start to talk about if I'm holding 2 CPUs in my hand, how do I compare them? How do I know which one is better? So better is kind of a relative term. Now, if I compared a CPU from 1970 to a CPU from today, you could probably say that the one today, probably across the board, is better. But comparing 2 CPUs that were kind of made at about the same time, it's a little bit more difficult. So there's these different competing factors. There's what's known as the clock speed. The clock speed is a little bit, unfortunately this semester, since we have the reduced lecture, normally I do a whole diagram of what clock speed means. But we have this idea in electronics of what's known as the clock. So imagine that you are looking at a clock and you see the second hand going around. Okay? So it's literally like that. You have this idea of something happening at exact intervals. On the clock up there, it's every 1 second. But on a CPU, it's very, very fast. Just to use round numbers, let's say it's 1 billionth of a second. So a 1 gigahertz CPU would be, it would be doing, instead of having the clock go around every second, it would be going around 1 billion times per second. So the way we design CPUs is that each tick of the clock, we can only do one thing. It's just how they make the electronics, that we can only do one thing during that clock cycle. So imagine the clock on the wall. I could only do one thing. Okay, I can add up two numbers, and then I wait, and oh, next second, let me take those two numbers and then divide by 2, and then take those couple of numbers and then compare it to another number to see if it's greater than or less than that number. Same thing on your CPU, is that it does very, very simple operations, and it does those a billion times per second. But again, we can only do one thing per clock cycle. So if we finish with extra time, then we're just sitting there doing nothing. And it's this balance, because some things we can do really quick, like add two numbers, but some things might take a really long time. And so then we have to say, okay, really our clock speed is based on the slowest thing. Now they come up with very clever ways of sometimes they can break it up, but you get the idea, is that if we make our clock speed too short, there's certain things we can't do, but if we make it too long, where we can, then we end up in the situation where a lot of the CPU cycle is wasted. Now, in the 90s, there was this battle. It was called the Megahertz Wars between AMD and Intel, and probably other companies, but they were kind of the main ones, where you can come up with various gimmicks to make it seem like you've got a very fast clock speed. Because if I go look at two computers, or two CPUs, and one is 2 gigahertz and one is 2.2 gigahertz, you might assume the 2.2 gigahertz is faster. But they came up with all these games to chop up their different CPU instructions to make it look like I'm running at a very fast clock speed, but that's not really what's happening. Okay, but in general, the idea is that if I've got two CPUs that are essentially the same, and the only difference is the clock speed, the one with the higher clock speed is going to be the faster CPU. But at the same time, we also have the need for running multiple programs at the same time. This is very true in scientific computing. If I'm running some sort of traffic simulation, imagine I'm an engineer working for the state, like the I think it's called Department of Transportation even at the state level, but imagine I'm working for the Department of Transportation, and they do all these different traffic simulations. So if I run this traffic light for 30 seconds versus 35 seconds, how much traffic is going to go through? In that case, I might want many, many cores, because I have to track all these different cars going through the light. Okay, if I'm doing a simulation, I want to track a car, and so we might not actually need a very fast clock speed, because it's doing a very simple task, but we want to be able to do a bunch of these things at the same time. So it depends on the task. So in practice, we've got all these different competing things, clock speeds, multiple cores, but then we also have things that aren't even related to how fast the chip is. What's our main concern on a mobile device about the CPU? Is it how fast it is? Not usually. We care a little bit. We want a fast phone, but what's usually more important than the speed? Well, that too. But how much power that CPU uses? Because if I tried to stuff a desktop CPU into my phone, I'd probably get about 20 minutes of battery life. It'd be the most useless phone ever. So we have all these different things that we're trying to balance. Yeah.
And also, a lot of people get caught up with the benchmarks for phones and which sensor performance is the best. But really, a lot of companies prove that you don't need a fast processor to make a fast phone. A lot of it is software.
Yeah, that too.
That uses a mid-range chip from Qualcomm, but due to the software, the thing that the phones like flies.
Yeah, exactly. 'Cause there's a lot of software is interesting, because there's a lot of perception. Like when we were talking about interrupts, if I press a button, so imagine if I've got a very, very fast phone and I press a button and there's a slight delay, the phone feels slow, even though it might have a faster CPU. And so a lot of it is just like mental. Like if I press a button on the phone, it happens right away. The phone feels fast. And so you're right. You can solve a lot of things with software, which is very interesting, which is actually for a long time. I don't think this is true anymore, but in the early days of iPhones, what a lot of manufacturers of Android phones would do is they would throw as much hardware as they could at it as possible. And then Apple took a different approach. They said, let's use a mid-range chip, but let's try to do the best we can with that chip and do things in software. I don't think that's true anymore because they bought a company that actually manufactures chips, so I think they actually do have very fast CPUs now, but at one point in the early days of iPhones that wasn't true, but that's a very good point. So we have all these different competing things that we have to worry about. And a lot of times I'll get people at various, because I work with different people doing different things. So I might work with somebody who's just asks about a gaming machine, but sometimes I'll work with scientists and they'll ask which computer or server to buy. And really I don't have generally a good recommendation. What do we have to do? We have to do this idea of a benchmark. You take the thing that you care about the most, and then you compare that on a bunch of different system setups. Okay, so for most consumers, to be perfectly honest, when most people are buying a CPU, or not a CPU, buying a system, let's say from Best Buy, usually they just go by the salesman's recommendations. But once you get into the professional world of like, I'm a scientist, I have a budget of $20,000, I need to buy a server that's really good for something. Usually what we want to do is rely on this idea of benchmarks. Do I need a really fast CPU for this? Do I need many cores? Do I need very fast memory? Can I get, so hard disk drives are generally much cheaper but slower, but it may turn out that the type of data I'm working with is small enough that it doesn't matter, so the extra cost of an SSD isn't really worth anything. So we go through these things called benchmarks. And the idea is to compare a bunch of different systems doing this specific thing, let's say a weather simulation, and we say, okay, of these 5 different systems that I'm comparing, which one completed the weather simulation fastest? So rather than looking at raw specifications, we just say, hey, okay, I don't really care about these specifications. I want the thing that's going to do this task the quickest. Now in practice, I think most people realize that it's not really practical to go out there and buy 5 systems and compare them. So what do we typically do instead? These days, what people will do is when they buy their computer, not everybody, but enough that what they'll do is they'll load there's a few different companies, but the little piece of software where you can benchmark your own system, and then you upload it to a website, and then they create a database. So it looks at all your hardware, and then it says, okay, let me look at these different benchmarks, and then if you're going to buy a system, you can say, okay, I'm looking to play this specific game, which benchmark was best for this specific game. Now I will tell you, it's not all honesty in the benchmark world. Many of these hardware manufacturers have gotten caught over and over and over again lying on not lying, but what they'll do is they'll put special code inside of their drivers, and they'll try to detect, let's say a specific game is playing, and what they'll do is they'll say, oh, okay, they're playing this specific game. Let me take all the resources from the rest of the system and let me just dedicate it to this one game so I perform well in this benchmark. So in the benchmark world, it's not all honesty, but for the most part, generally that's what people look at, is like they'll look at benchmarks and say, okay, I'm looking to buy a system. Which system performed well on this task? Okay, and that kind of takes care of question number 5. It's just because, kind of to summarize, it's very difficult to compare 2 different systems because there's so many different ways to measure a system. And really the best way to tell which system to buy is just to do benchmarks on the thing that you're going to do most often with that system. Let's say, for example, if you're buying it for gaming or for weather simulations or for whatever, and you just look at, hey, other people have bought this system before. Let me look at how fast it was able to complete that task using benchmarks. And then I think the very last thing we'll do today is we'll look at this slide. I can find it. There it is. I already started to talk about this and allude to this, but this pyramid right here is very good. I already mentioned, so there's this relationship that we can have something that's very large, but by making it large, it's in general going to make it slow. Or I can have something that's very fast, but in general, making it fast is also going to make it to where it has very little storage. A CPU, what's called a CPU register, is actually only a few bytes. And we typically have like, maybe around 15 to 20 CPU registers on a CPU. So here we're dealing with a few bytes versus a hard drive. I can go on Newegg right now and probably buy a 10, 12 terabyte hard drive for, a few $100. But it's going to be very, very slow in comparison. Like what we call orders of magnitude. And what we do is, remember the main three things that we're worried about is CPU, RAM, and then our storage device. So either an SSD or a hard drive. At the top here, we see CPU, and I already mentioned that it's very small storage, but very fast. The next level up that we have is our RAM. And so RAM we usually talk about in the order of gigabytes. So you might have 4 gigabytes or 8 gigabytes or 16 gigabytes of RAM on your system. And that's going to be much faster than your hard drive, but much slower than your CPU. And that kind of sits as a middle ground. It's like your temporary working area, that we pull things from the hard drive and it sits in RAM waiting for the CPU. And then all the way at the other end, again, like I mentioned, we measure hard drives in terabytes. Now you might ask, well, what if somebody could come up with a magical device that was both fast and large? What ends up happening is once we come up with one of those devices, then we just get rid of what it replaced. Okay? So we've seen that in the history of computing, is that maybe before we had hard drives, we would have these tape-based systems. And once hard drives became both larger and faster than these tape-based systems, we generally got rid of them. We still use tape backups for other reasons because they store very well. But the idea is that if you come up with something that's better in both things, that it's both faster and has more storage, it just gets rid of the thing. We don't really keep it in the pyramid anymore. Again, there might be specific reasons, like it's very cheap or it archives for a very long time or something like that. But in general, we would just take it out of the pyramid. Now, what we've realized over time is that we can sort of cheat a little bit. We can have this idea of a cache. So we'll notice that between the CPU and the RAM, so CPU is in the order of bytes, RAM is in the order of gigabytes, we have this idea of a cache. We have different levels of cache, but let's just fold them all into one. We'll just say cache. So let's talk about the idea of a cache. If I'm doing something, let's say for example, I'm just reading a book. That's a perfect example. So I open up the book. After I read a page of that book, what are the chances that I'm going to skip to a completely random page versus I'm going to turn to the page and get to the next page? Let's say there's a 99% chance that I'm probably just going to turn to the next page. Now there are some times I may actually just go to a random spot. I may just want to have read something out of the book for one page, and maybe it refers to something else. But most of the time we're going to read a book one page at a time. The idea of a cache is that we're going to be doing things that are very predictable. So we have this idea of, I don't want to use too many technical terms, but the idea is that if I'm looking at a page in a book, I can take the next couple of pages off the hard drive and then put them into cache. Does that make sense? So rather than having to go all the way back to the slowest way of retrieving things, I can say, okay, they're on page 89. There's a really, really good chance that the next page they're going to go to is page 90. So without them even asking, let me take page 90 and let me put it in the cache. Does that make sense? So there's this idea of what's called temporal locality, that over time, I'm going to, I shouldn't use these technical terms, but the basic idea is that if I grab a piece of data, the chances of me getting another piece of data nearby are very good. So what I do is I take that and I put that inside of the cache. There's this other idea that if I get a piece of data, I'm going to want that data again. So imagine if you are on your computer. You may have, especially for those of you, how many people have a lot of games installed on your computer? Like, of those games, how many do you play on a regular basis? Yeah, a couple, maybe less than 10%. Could we all agree? So of the things that are available, there are going to be things that we're doing over and over and over again. So the idea of a cache is the same thing, is that there are certain tasks that I do a bunch of times versus things I do very, very rarely. Imagine it on your computer if you've got thousands or tens of thousands of pictures that you've just taken over time. What are the chances of you looking through those pictures? You might do that a few times a year, but for the most part, you're not going to be going through all 10,000 on a daily basis. But what other things are you going to be doing on a daily basis? Opening a web browser, opening up your favorite game. Okay, and that's the basic idea of a cache. You might think of websites. Think of all the different websites that are out there. In practice, how many websites do you usually visit on a given day? Probably very few. Maybe your school-related websites, your work-related websites, any message boards for games or something that you play. Every once in a while, you might visit another website for like a very technical or out of the ordinary piece of information. But for the most part, you're actually going to be visiting the same websites over and over and over again. And that's the idea of a cache, is that we put something kind of in between the CPU and the RAM. And caches exist in all different ways. But in this specific pyramid, let's just concentrate on the cache between the CPU and the RAM. So I've got the CPU, which is very fast, and it's measured in bytes. I've got my RAM, which is slower, and it's measured in gigabytes. These caches are smaller, and they're usually in megabytes. So let's say, for example, I've got 64 megabytes of cache, and the idea would be, okay, this person is doing the same stuff over and over and over again. Let me just put that in the cache. I don't need to store it all the way back in RAM because the chances are that they're going to use it again. Or the other alternative that we talked about before is that if I'm getting a page out of the book, the chances that I'm going to read the next page are very good. So if I grab a piece of data, let me also grab, even though they didn't request it, let me grab all the data around it, put it in the cache, because statistically there's going to be a very, very good chance that they're going to want the data in the future. Okay, that's the idea of a cache, is it kind of acts like it is an in-between, where it's smaller. It's kind of in between, so it's larger than a CPU, smaller than RAM, slower than the CPU, but faster than the RAM, and it handles the most common cases, because you don't need to handle every case. Just the way the world works, it's called the Pareto principle, is that 90% of the time you're, let's say, for example, if you're using Microsoft Office, we've got all these different features. 90% of the time you're only going to be using 10% of the features. It's that same basic idea, is that most of the time you're going to be doing a very small number of things. Let's make those small number of things as fast as possible. Okay, and that's the basics of this. Now we do have other things in between, but for caches, let's just say for now, just to keep our lives simple, let's just think of the caches that sit in between the CPU and the RAM. Okay, so I think that's a good stopping point for today. Let's just talk about what we've covered. So you should just already know this. I don't want to flat out give the answer, but we've said these two names many times in class today. And again, desktop CPUs. Other types of CPUs like phones and other things, that's a different world. Let's just concentrate on desktop. We talked about Moore's Law. We talked a little bit about hyperthreading and multi-core systems. We just talked about this. We talked about this. And then the next, and actually we talked about 8. We talked about caches. So next class I want to get into some other bits of hardware like RAM, hard drives versus solid state drives, all the different considerations on that, okay? So any questions on this? So let's do